Good morning. For today's lecture, I'm finally going to get into some really serious mathematics, at least beginning some really serious mathematics, talking about multi-stage optimization and dynamic programming. But before I do that, I still want to go back to the big picture, because we always have to put this stuff into context in the big picture. So let me go back a bit to this cognitive map for the course of all of the optimization methods that are out there. In this course, I'm mainly going to focus on optimization methods developed in three core communities: control theory, operations research, and computational intelligence. And before I get into details, I need to say a little bit more about these communities, because these are the places where you go to get more advanced current information about these methods. So to start with, I already spoke a little bit about control theory. I mentioned that modern control consists of three main parts: optimal control, which is up here and here. There's also robust control. I mentioned Sipkin and the worst case planning, and adaptive control, which I'll talk about more. There are also older kinds of control. Now, where does control theory live in this world? I would say that the core place for the development of advanced control theory, at least in the United States, is within the IEEE Control Systems Society. I hope you know about IEEE. You certainly should by the end of this course. IEEE used to stand for the Institute of Electrical and Electronic Engineers. But then it got broader and broader as people started working in aerospace and computers, and now it doesn't stand for anything. It's just IEEE. It includes electrical engineering and a lot of related disciplines. It has more than 400,000 members. It's the world's largest professional society, and it has a lot of journals. And one reason I mention that is IEEE, in addition to having the Control Systems Society of IEEE, also publishes a journal called the Transactions on Automatic Control, and that's the leading journal for mathematical results in the field of control theory. They also run a conference called the Conference on Decision and Control, CDC, every year, and that's the focus of the Control Systems Society. In the National Science Foundation, where I've been working for the last 25 years in the electrical engineering division, there has been a program funding core research in control theory, particularly the IEEE community, for more than 20 years. But control engineering is not only the property of electrical engineers. There's a major group of people in applied mathematics who prove theorems in that area, and there are other journals, but a lot of them aim at the transactions on automatic control. But there are also people in chemistry, chemical plants. Of course, the petrochemical industry, the oil industry, the chemical industry, these are very large industries, among the biggest in the world economy. And it takes a lot of sophisticated control to know how to run a very large chemical plant without it blowing up. And I'll be talking about those guys for a while. So the chemical engineering community does develop some new mathematics in the context of their applications. And it's a struggle to make sure the lessons you learn in chemical engineering connect back to the basic mathematics. Communication between those communities is a big issue. And at NSF there is a chemical and biological engineering division, and they have their control work they fund. What's more, the aerospace community funds a lot of work in control with high-speed aerospace, hypersonics. Control is one of the really crucial enabling technologies. Companies like Lockheed and Boeing probably fund more PhD control theorists than anybody else in the world, although the auto industry works a little bit with them too in similar areas. And so naturally, in the world of mechanical engineering, there are people who study practical control problems from their community. And you can even go all the way to the American Institute of Aeronautics and Astronautics, AIAA, Or you can go to their Guidance, Navigation, and Control Society. There are many people in that area also doing control. Primarily they're aimed at their specific applications, but again it comes back to the basic mathematics. And sometimes some of the best papers on the mathematics of control can be found in their application journals. As a result of all that, there is an annual conference called the American Control Conference, which brings together people from all these different aspects of control theory to discuss what they've learned, connecting theory and practice. So there's a lot of other work in control theory. I'll talk about it more. That's a major discipline. Another major discipline here is operations research. You'll notice on the right I mentioned terms like linear programming, nonlinear programming, unconstrained optimization. Those are basically things from the operations research community. Back when I was going to school, there was a community called the numerical analysis community. I assume it's still there. It's more part of applied mathematics. And when people wrote books on unconstrained optimization algorithms, a lot of that would come from the numerical analysis community. But to a great extent, this new operations research community, which kind of grew out of the linear programming boom of a few decades ago, the operations research community has grown and it's become the major center of a lot of these types of methods. Back when I went to school, there was a joint meeting of the Operations Research Society of America, ORSA, which was developing things like linear programming, and the Institute for Management Science. Well, management science, that speaks for itself. They had a joint meeting every year, but that turned into a meeting called INFORMS, INFORMS, which is the _1 meeting every year for bringing together the algorithms from operations research, like nonlinear programming and a lot of approximate dynamic programming. And it's become one of the major centers for that kind of work, the Operations Research Society. And of course, they tend to address problems more like industry planning, logistics, managing whole companies. There's a group at IBM that uses these kinds of methods to come up with corporate strategies for companies to manage at all levels. So that's another major community, which I'll talk about more. I might add, some of that stuff goes on in economics, but at NSF there are at least 1 or 2 research programs dedicated to operations research in the engineering directorate where I work. Somehow or other they ended up in civil and mechanical engineering, but in electrical engineering we also fund some operations research, especially addressing the power grid. The electric power grid is a major challenge for optimization. Operations research methods are being used every day to allocate electricity all over the U.S., and I will talk about that. And electrical engineers from the power side are involved in that. And there is a Power and Energy Society in IEEE, which is the central focus for that kind of mathematics. Finally, last but not least, I will mention computational intelligence. That's really the area where I have the most credentials myself, personally. IEEE has a Computational Intelligence Society, which is now a very large society. But when I started up at NSF, it didn't exist. Back around 1988, IEEE became very interested in the neural network field. That led to a Council on Neural Networks, which became a society. But at a certain point they said neural networks are an important area of technology, but they have cousins. And there are 2 other areas of technology especially that were of interest to electrical engineers who were doing neural networks as well. There's an area called fuzzy logic, and there is an area called evolutionary computing. And the Computational Intelligence Society was originally incorporated to bring these 3 communities together for engineering technology applications and also related interesting areas. So the evolutionary computing area I've mentioned over here. There are a lot of stochastic methods inspired by genetics, genetic algorithms, which address the problem of how do you find the maximum of a very complex known nonlinear function. Okay? So these are methods which address single-stage deterministic optimization. But when life is not complex, they can be very hard. I should define this term convex. For our purposes, a convex optimization problem is one where you're maximizing a function where the graph basically has a single hill and you can get to the maximum by going uphill. Convex optimization, it's a problem where you can find the maximum of a function just by following the gradient. By going straight uphill, there's only one peak. Non-convex problems are where you have a whole lot of hills, and the problem is how to find the best global maximum in a very complex space. Non-convex optimization is much more difficult than convex optimization. There are lots of methods that work well if there's only one hill, if there's one local maximum, which is also a global maximum. But a lot of times in the real world, it just doesn't work that way. A lot of times we have to solve problems where there are many local maxima, and for those problems you need to worry about your abilities in non-convex optimization. One way to deal with that problem is to just search randomly in the space of possibilities. And that's kind of scary, stochastic search, but sometimes we have to do that. And then the question is, can we do a good stochastic search? Well, evolutionary computing and genetic algorithms are examples of methods to try to do stochastic search effectively. And they have a lot of real-world applications. They are one of the 3 core groups in the Computational Intelligence Society. And they have their own journal. But the neural networks community is the one that I'm more involved in. I also work with the fuzzy logic people sometimes, but that's not going to be a big part of this course. I'll mention a little bit about how fuzzy logic can work together with neural networks. But mainly I'm going to focus on the neural network and evolutionary computing aspects. For neural networks, optimization is not the only thing we do in neural networks. And I do hope everybody will learn something about neural networks by the end of this course. There are a lot of different definitions of what the neural network field is. You can look at the journal to get some idea. There's another journal called Neural Networks, which comes out from the International Neural Network Society. It's an Elsevier journal. Those are the 2 leading journals in the field. The Neural Network Society was developed as a new cross-disciplinary activity that's inspired by brains, works with neuroscience and psychology, but tries to develop mathematical models that you can use either for decision making and engineering, or use them as models of how brains work. So this entire course is basically addressing the technology aspect of what I view as a bigger field, which I now call cognitive optimization. I didn't come up with this term myself. This came up as a result of discussions all across the engineering directorate of NSF. Back in 2008, we were talking about where are the emerging fields, new opportunities for engineering of greatest importance to the world and to basic science. And in that year, NSF came up with seed funding for a topic called COPAN, Cognitive Optimization and Prediction. If you go to the NSF webpage, you can see exactly what we were looking for, exactly where we see this research opportunity. I encourage you to look at that. It's only 2 pages, and there was a whole lot of thought that went into that, bringing together people from all types of engineering and biology. The basic idea is we want to understand and replicate how brains learn over time to do a better and better job at solving the optimization problems they confront and the prediction problems they confront. For optimization, it's pretty simple. A mouse needs to maximize the probability that it survives as it goes from here to the cheese. And that's not an easy problem. How do you build a system that learns to maximize the probability of survival in an environment where there are no guarantees. If you wanted to use robust control like CLION on that problem, you would just throw up your hands because you can't guarantee survival. The worst case is that you're dead, and that's that simple. And if all you do is consider the worst case, you just lie down and die. So you need to do something more like maximizing the probability of survival. That's an optimization problem. But it's not enough to have optimization. In those decision trees, you may remember, the quality of your output depends upon putting in the right utility function and putting in the right probabilities. In practice, when we use optimization methods like ADP, the quality of the results depends on the quality of the assumptions we make about the probabilities that we're facing in the real world. And it turns out there's a whole other stream of research, which we now call cognitive prediction, which addresses how can we learn those probabilities? How can we learn to infer what's going on out there in the real world? And that's not an optimization algorithm exactly. That's, in a sense, more like statistics and forecasting and probability. In an ideal world, this course will be accompanied by another whole course for at least a year that will address how do we get better probabilities, how do we get better prediction. Even in control theory they face the same issue. If you have a bad model of your plant, you're going to come up with a bad control. So there is the control aspect, maybe optimal control, and then there is the system identification aspect. In control theory, they call this system identification. And it involves more than just prediction. It's also trying to understand what is the state of the world, what are the probabilities. So these are two major streams of research. This course is just going to focus on this stream. There are also many applications of this work. There are technology applications I'll talk about. Where I came up with this is really my favorite chart. This could be the poster I put in my room to symbolize all of this stuff. A guy from China asked, what are the major streams of research that are important for the future? And I said, well, I see these two big rivers, but these rivers themselves are based on a merger of many mathematical principles. We come from the high mountains of mathematics, pouring down, coming together to these big rivers. In the realm of mathematics, you can see this as a symbolization of the Bellman equation, which I'm going to talk about more. There are other methods, and this is something called the chain rule for ordered derivatives. I don't expect you to know what an ordered derivative is. You're going to have to know what a partial derivative is to make sense of this when I explain it later. But this is basically an equation I came up with years ago and proved. I call it the chain rule for ordered derivatives, and a lot of people call it backpropagation. It is a universal method for calculating the derivatives of anything you're interested in with respect to all of the inputs and parameters of a complicated nonlinear system. It has value in both of these streams. It's critical to nonlinear control. There are a lot of people who say they know about backpropagation and they don't even know what it is. It's a very critical tool as part of this larger picture. So now what I'm going to do is move on to something more concrete. We're interested in cognitive optimization in this course. We're interested in multi-stage stochastic optimization. And now I'm going to set up some mathematical notation. Okay? To begin with, when I talk about multi-stage optimization, in this course I will consistently use this notation. Little t goes from 1 to big T. T is the final stage, the last stage of the decision process. 1 is the first stage. If you were in operations research, this could be pretty easy. If you're trying to find an optimal schedule of sending out trucks for the next week, you want to know how many trucks to send out every day? Well, every day is a stage. So the decision problem is, how many trucks today? How many tomorrow? 7 days in the week. Capital T is 7. It's a 7-stage decision problem. And each stage is a time. It's a day of the week. But on the other hand, there are other applications of multi-stage decision. When you looked at that decision tree for the oil company, the first stage was to decide drill right away, give up, or buy seismic information. And then the next stage, eventually, depending on the seismic information, you decide then whether to drill or not. So it's a two-stage decision problem, but the two stages aren't exactly time. Well, in fact, the mathematics I will show you of multi-stage decision-making doesn't really require that the stages are discrete time intervals. In fact, there's a lot of work on Markov chain decisions which involve discrete events, where each decision point results when an event occurs. And it's still the same mathematics. You can still label it, from 1, 2, 3, the same T stages, as long as you get the math right of the transition from one stage to the next. You can use the same Bellman equation. So that's another way of applying it. Because this mathematics is so general, there are a lot of people who won't even use the letter T. They'll use the letter K to emphasize stage 1, stage 2, it might be time, it might not be time. But I'm going to use the letter T. I'll tell you in advance it might not be time. It's more general mathematics. But calling it T helps you remember it's kind of like time, and most of the time it does represent time. So I'm going to talk about multi-stage decision problems where T equals 1 to capital T. Now, let me emphasize that's not the only work that goes on in control theory or RLADP. There are many times in control theory when people talk about continuous time. In this course, I will give you the discrete time version of the Bellman equation. But there is another guy I promised to talk about more called Frank Lewis, and some students of Lewis and some others following on, who have been developing RLADP in the context of continuous time. And a lot of adaptive control has been developed for the case of continuous time. They started out with differential equation, ways of describing the world. If you want to learn about the continuous time versions of RLADP, instead of going through to the end of this course, you might go to the book edited by Lewis and Liu, the Handbook of RLADP. It's a new book, 2012, which comes out from Wiley and IEEE. Okay, at the end of the year. And in that book, Frank Lewis does have sections describing the continuous time versions of ADP. A lot of this course is based on my chapter in that same book, which is chapter 1, which gives an overview of all this material. So I highly recommend that book. It's one of the primary sources in this field. Now, having looked at Lewis's work, it's my impression that the results you get in the continuous time area are not so different from the discrete time. And the discrete time is a little easier to represent, and that's why I'm going to give you discrete time in this course. It's my impression that if you look at the discrete time methods and consider the limit where the time interval goes to 0 for the fast ADP methods, they pretty much converge to the same methods that Lewis has come up with in the continuous time case. So there's not a dramatic difference. You won't have to relearn everything. They're closely related, and it's important to understand the relations. I should say one more final thing on this issue of control with discrete time and continuous time. There is a classic book by Astrom. People used to tell me that Narendra of Yale and Astrom of Sweden were the two leading gurus in the world in the field of adaptive control. Though there are a lot of other people in adaptive control who might question that. Lewis himself has done a lot of important work in adaptive control. But Astrom's text on adaptive control is one of the #1 sources in that field. Astrom has also written a book called Computer-Controlled Systems, where he analyzes the difference between discrete time and continuous time representations in enormous detail. In the modern world, we have to use discrete time more and more because we use computers. That's what Astrom addressed. And he asked, how much do we lose when we use computers instead of using things like the ideal perfect capacitor in a circuit to do an analog time decision? And basically, if you follow a few basic principles, you're okay. Astrom describes what they are, And mostly today we use discrete time, but it's important to understand how it could go wrong, and if you're worried about that, those guys will help you. Now there's an interesting question. If we're trying to understand the brain, as I am, what does the brain use? Does it use discrete time control, an ADP, or does it use continuous time? Long ago I remember an interview with a neuroscientist where somebody asked him about that. And he said, people will sit there and they'll worry. They'll have 5 different theories of how the brain could compute something. And if you study how the brain does it, usually you'll find out the brain uses all 5 plus another 5 you never thought of. And that's basically true here. I've been studying how this stuff maps into the brain, and it turns out there's good evidence that there are parts of the brain which use discrete time. There are clocking circuits in the upper levels of the brain. The more intelligent parts of the brain are highly dependent on clocking circuits. If somebody tells you the brain is a perfect example of discrete time, of continuous time, asynchronous processing, they need to go back and study their neuroscience. There are a lot of modelers who believe that as a kind of religious belief. It's a very deeply held belief, but it's not true. And we have known in neuroscience for like 30 years that there are clock circuits that are absolutely essential to the higher levels of intelligence in the brain. If you want to know more about that, I have a couple of papers in the journal Neural Networks, not Neutral Networks, Neural Networks, in 2009 and 2012, and I cite a few sources for you in things like the Rockefeller series and the annual reviews of neuroscience, where they describe these clocking circuits in great detail. But on the other hand, the lower parts of the brain have to make very fast decisions. You know, football players, you got to have a resolution of like 200 actions per second, 200 hertz, to have good, smooth control catching a football. And for those very high-speed circuits, they really don't have clocks. They have to move very quickly. So there are fast circuits in the brain that basically use continuous time, but you can use discrete time mathematics to capture the same algorithms. And then there are other parts that are basically discrete time, and they have to interface between the two of them. What's more, there's an issue about discrete variables and continuous variables. Does the brain use continuous variables, like most engineers, to describe the dynamics of the universe? Or is the brain a digital system, where it's discrete choices, yes or no? And it's very clear the brain uses both. And it's very clear that the ultimate goal in engineering and technology is going to have to be to learn how to deal with systems, hybrid systems, where some variables are discrete and some variables are continuous. In today's research, we're still working on nailing down the best mathematics for those two cases. The best way to bring the two together, it's not going to be simple. There have to be a lot of ways to connect the discrete and continuous world. And today, in this case, I'm mainly going to be talking about continuous methods and discrete methods. And there's a limit on how far I can get you into the hybrid, because more research is needed in the hybrid. But we have learned something about hybrid systems. Finally, when I talk about t equals 1 to capital T, I haven't really told you all the details. The discrete time approach from 1 to capital T is actually a very general approach. There are 3 special cases of this which are very important in practice. There are some special cases where you know capital T. I gave you an example from operations research. You're planning ahead for 7 days, each day is a decision, capital T equals 7, and that's the end of what you want to think about. That's a finite horizon decision problem. You know the horizon. That's a very important special case. But there's another special case where you continue the decision forever. For example, if you're designing a simple regulator, like you want to keep an airplane from crashing, and you want to put a kind of a regulator to keep it within bounds. Well, you want that regulator to stay on as long as that airplane is in the air. There are many cases where you're designing a regulator system to continue basically forever, indefinitely. And in that case, your final time is infinity. And there are times when, in principle, you don't want to look ahead a finite time horizon. You want to know what are the benefits you get as far ahead as you can possibly see. So that's the special case where t is infinity, an infinite time process. That's a very important special case. A third kind of special case is when there is a condition for stopping. For example, if you design a missile interceptor, capital T is when you hit the target or when you have no chance of hitting the target. It's an event-based or condition-based termination. The general equations I'm going to give you for dynamic programming apply to all three cases. But when you nail it down to specifics, the details are different, of course, depending on which of those three cases it is. Infinite horizon, fixed horizon, or conditional horizon. So now, I'm going to start getting into some real mathematics. And of course, I hope you have the handouts. I hope you're going to be able to refer back to these things. First, I'm going to define some notation. Other people use other notation. There are four important letters I'm going to define here. J, R, pi, and gamma. These are fundamental to all multi-stage optimization, whatever the field you're in. As I say, though, people use different notations. In terms of what is optimization, there are people who say, gee, do I really want to do it the optimal way? And I say optimization means doing the best you can. Of course you want to do the best you can if you can. Optimization is pretty much what we always want to do when we have some idea of what we want to accomplish. The concept of R represents interest rate. Let me briefly say, R is interest rate, pi is called policy, gamma is called discount factor, and J is just J. I'll define it here. The interest rate R is an idea that came from economics. It's a central concept in economics. The interest rate and the discount rate are very closely related. They're basically the same thing. The original concept in economics is the concept of present value. In investment and finance, this is one of the most fundamental concepts, present value. If you have a stream of future dollars coming in from an investment, sometimes negative when you have to invest up front, that's a cost, sometimes positive when you're making money, to figure out whether you're making a profit on balance when you consider the costs in some years and the benefits in other years, you estimate the present value. And the present value is the stream of net revenue over all future years or as far as you're looking, discounted by interest rates. Because if the benefits come too far in the future and your investment is up front, sometimes you're better off just putting the money in the bank and collecting interest. So whenever you make an investment decision, you have an interest rate R, you discount the future by that interest rate, R. But the algebra is easier, if we define a new quantity gamma, which is just 1 over 1 plus R, and put that in the equation. Most of my early papers, I use the interest rate because the connection to economics is so important. But here, for simplicity, I'm going to use gamma a lot. That's what people in computer science tend to do. And I guess even in operations research, a lot of people are using gamma these days. And gamma is just defined as 1 over 1 plus R, and we use it just to make the algebra look easier. So it's called a discount factor. If you care about the future, perfect foresight, if the future is just as important as the present, that's like a zero interest rate. You don't discount the future. That's like gamma equals 1. Gamma equals 1 means you really care about the future. If gamma is 0, it means you only care about the present. And when you pick gamma of 0, that's like an infinite interest rate. And when you pick gamma equals 0, you're not doing multi-stage decision anymore. You're basically saying the future doesn't matter beyond the present stage, and all you're really doing is maximizing the present stage. So gamma can vary between that 0 and 1. Now, because we use interest rates and discount factors in ADP, we really need to know what they mean. These are not just fudge factors to help you convince your boss you did something. It's really important to know what they mean. In economics, the interest rate which you pay to the bank is basically the sum of two parts. There is a core interest rate, which represents the idea that $1 in the future is worth less to your bank than $1 in the present. That's what the bank cares about. It's sort of the utility function of the bank. The bank doesn't think $1 in the future is worth as much to them as $1 in the present, because they could make money investing it in the present. That's the core interest rate. But when you pay interest to the bank, you also pay something called a risk premium, which represents the fact that the bank is not certain that you will actually pay back what you owe. Now, the subject of interest rates is really huge. It's hard for me to resist talking about it because it's so important to the world economy, but I will resist. What I do want to say is that people have extended this concept of interest rate from economics to optimization. In a way, it's just an analogy. This is kind of a brute force thing we're going to do, but we all do it. The idea is, with utility functions, we can attach a discount factor not just to dollars, but to utility functions. And the interest rate we apply to our utility function represents how much we care about the future. So that in multi-stage decision problems, it is now conventional to say, your goal in a multi-stage utility function is to maximize this thing I'm calling J. You're trying to maximize the whole stream of future U. Now, when we define it this way, U suddenly isn't what you really care about. U suddenly becomes your happiness or your payoff in a time period. J really represents your total happiness across all future time. And J doesn't have to be a weighted sum of future U. That's basically just a kind of convention, but people have found it's a pretty workable convention. So when we do multi-stage decision problems, we need to know, what do we want? What do we want the system to produce? That means, what do we really want to maximize? And what we really want to maximize is a sum over future time. And to make this meaningful, we have to say, what is the U? What do we care about in a given time period? What is the payoff or the happiness we care about in each time period? And then, how much do we care about the future? How do we want to discount the future? So when I talk about multi-stage optimization, I'm going to do what pretty much everybody else does. I'm going to look at this kind of a function. But I need to define this formula a little bit more closely. In this formula, I've told you what is a gamma, what is a t. I've told you that U is your action, X is the state of the world, and I'm assuming you know the state of the world at each time period. For now, I'm assuming it. Later, I'll come back to that assumption. But I haven't defined what is a pi. Pi means a strategy or policy, a strategy of action. Von Neumann used to talk about finding the best strategy of action. I haven't gotten back to see how Bellman phrased it. But nowadays, people often use the word policy. That's more standard in the operations research literature. And that notation is catching on, but I still sometimes call it a strategy. And what it is, a policy is what you're going to do at any time period in the future, depending on what happens to you. So having a policy means that you decide what actions you're going to take as a function of what happens and what time it is. So in dynamic programming, what we're trying to do is to find the best strategy of action. What should you do depending on what happens in this uncertain world? So you're looking for the best strategy of action. What happens in the future depends on your action. You don't know what x of tau is going to be in some future time unless you know what you're going to do. If you change your actions, you'll change the future. And you don't change it in a deterministic way. It's the expectation value. The expectation value that you're trying to maximize. So you're trying to find a strategy of action of what to do when, which depends on what you can see and on what time it is, as a function. Well, you want to maximize your future happiness as a function of policy. You want to find the best policy. Now, let me emphasize this is not as specialized as it might seem. I mentioned there are stochastic decision problems and there are deterministic problems. This formula is valid in the deterministic case as well, but in the deterministic case, there are no probabilities, there's no uncertainty, so you get rid of the brackets. It's the same formula, but it's simpler because the brackets disappear. What's more, well, let me talk a little bit more about interest rates, because that's an important part. When you set up the problem, you really got to decide what your interest rates are. So I'm going to talk in some length about this problem, about how should you pick your interest rate or your discount factor. There are many multi-stage optimization methods you're going to find in the literature where you don't see an interest rate or a gamma. For example, there are papers on something called model predictive control. That's a very important multi-stage optimization method, very popular in the chemical industry, model predictive control, and you usually won't find an interest rate in any of those papers. And the reason why is they usually assume the interest rate should be 0 and gamma is 1. And in a lot of my early papers on RLADP, the first papers out on heuristic dynamic programming back in '97, dual heuristic programming, globalized DHP, in all of those early papers, I didn't even include an interest rate because I didn't think it was really necessary. There are many cases where the right choice is the interest rate should be 0 and gamma should be 1. There are many cases where you don't want to discount the future. In fact, let me emphasize, your choice of R, just like your choice of utility function, should represent what you really want the outcome to be. But there are many people who use interest rates because they can't answer the question they really want to answer. There are times when people take certain methods of approximate dynamic programming or dynamic programming itself, and they try to apply dynamic programming to some problem and they can't make it work. They can't get it to converge. Now, the best thing is to find a better method. But if you can't get it to converge, a lot of people have noticed, wait a minute, all I do is add an interest rate. And sometimes that makes the problem easier to solve. In fact, if you make gamma equals 1, you've got a single stage optimization problem. You can use off-the-shelf methods for that. It makes life easier. But you're answering the wrong question. If somebody asks you to make a decision for how to maximize profits over the week, and you pick a gamma of 1, and all you do is maximize revenue over the first day, you're not answering the right question. And there are a lot of people who do that, and I've spent a lot of time trying to get people to answer the right question, the question that really matters. However, well, let me talk about what economics says. In economics, there's a lot of debate about what interest rates should be. I think it's pretty clear that the core interest rate, without the risk penalty, really shouldn't be more than 6% a year. Now, if you think about 6% a year, what does that mean? If you're making decisions over seconds, hours, or days, then what you really want is an interest rate of 0. You don't want an interest rate greater than 0 if you're making decisions over seconds, hours, or days. Even in economics, I have a couple papers arguing that if you use the right utility function, reflecting human values a little bit more than naked dollars do, there's a good argument that you should use an interest rate of 0 even for economic long-term decisions if you are a sane and ethical person. That's a long story, I won't get into it. But there are a lot of times when you want the interest rate to be 0. But what happens when you can't converge at r equals 0? What happens when you can't solve the problem? In that case, instead of answering the wrong question, what you really need to do is answer the right question as best you can, and you can use interest rates larger than 0 as part of that. With a lot of iterative methods or adaptive methods, your ability to find the optimum depends on your initial values or weights. It depends on your starting point. This is true across the board, really. Certainly in operations research and even control theory, certainly in neural nets, It depends on your starting point. One way to solve a very difficult decision problem with an interest rate of 0 is to first solve the decision problem for an interest rate greater than 0, what you can do easily, and then use the resulting policy as an initial value for solving a more realistic version with a smaller interest rate. And then just dial down the interest rate till you come up with a solution for what you want to do. Intuitively, this can be like, in the beginning you are myopic. As you learn how to play the game, you can see a little further, and as you learn and adapt, you can converge towards a solution which really has more foresight embedded in it. So this is a convergence strategy, but there are other ways to do this same sort of thing. At some point I'll talk to you about a thing called the truck backer-upper, a fantastic success of neural network control done by Bernie Woodrow of Stanford. It's not ADP, it's a deterministic method, but you can have problems in the deterministic case too, when you got a highly nonlinear problem like driving a nonlinear truck to get where you want to go. And what he found out was he could converge to an optimal strategy by first finding the optimal policy or strategy for states near the goal. This is a case where T is defined by the goal. And then you train the system for a larger set of states farther from the goal. Step by step, you can build up a controller which can handle the nonlinearities of the whole problem and the whole range of solutions. And as I said, Woodrow's solution for that problem is way beyond what any other method has ever come up with. It's an amazing success on a very difficult challenge problem. So these two methods, dialing down the interest rate and adapting, or considering states near the goal, these really are capturing the spirit of what we were doing in those decision trees. You may remember, in the decision trees, we didn't have to worry about convergence. We started from the end state, worked our way back in finite time, each step is exact, and you get to the end, you've got a perfect optimum. You can do that because it's a feed-forward system. You only go forward from the beginning to the end, and you can go backward. When you go backwards from the goal to the start, there's certain guarantees. We can't do that in complicated decision problems where there are loops, where you can come back to the same state. We can't do that, but we can approximate it. And these kind of convergence methods allow us to get some of the power and speed that we have already for the simple feed-forward problems. And now there's one final thing I need to say about interest rates. What if you don't really want to add up your payments or payoffs at each time in between? And what if you don't care about your level of happiness and comfort halfway through? What if you only care about the end result? What if you want things to be as good as possible at the end of the day? What if that's your concern? Well, you can still fit this framework. No problem. This framework can handle it. And there are basically two ways you can translate your values into a utility function so that you can use this kind of multi-stage optimization. One way is that you can define your utility function, U, so that the value of U is 0 until you meet the terminal condition, or until it's the last time. The same mathematics will apply. There will be a lot of zeros in those calculations. But as you feed back your values, it will all work. That's what we did with decision trees. Another way to do that is to be a little clever about how you define your utility function. This isn't clever about how to make it easy to solve. This is clever about how to represent what you care about. For example, supposing you care about the GNP at time capital T. Supposing all you care about is the GNP at the final time, the last year of your horizon. In that case, you can define U as the increase in GNP from this year to the next. And if you maximize the sum of the increase in GNP from this year to the end, that's the same thing as maximizing the GNP at the end. You can do the same thing at each time period. You could maximize, you can pick your utility to be the growth of GNP, the logarithm of this ratio of GNP now over GNP in the last time period. And when you maximize the sum of this growth rate, that's the same as maximizing the GNP at the end of the day. So you can apply this kind of multi-stage optimization even when all you care about is what happens at the end of the game. So now I promised to do some real heavy mathematics. And on this slide, this is going to be the first thing that really looks like mathematics. In this slide, I'm going to give you an intuitive, not complete, an intuitive derivation of the Bellman equation. This Bellman equation, I mentioned before, Bellman equation is to multi-stage optimization what Maxwell's laws is to electronics. It is absolutely fundamental. I'm going to talk about this equation at great length because we need to understand it inside out. This is the fundamental tool that we will be using whenever we do RLADP, any form of it. It helps to know where the equation comes from, and that's why I'll give you an intuitive derivation. This is not going to be a proof of a theorem up to the standards of a good mathematician. Though I have to say I've seen a lot of proofs in engineering and physics that don't live up to those standards either. I'm going to give you an intuitive version of this, but there are formal versions of the theorems out there very extensively in the literature, and some of them are actually rigorous proofs. We started out with a definition that j, as a function of x and pi, is this expected value in the future. It's basically your present level of u, or happiness, plus the sum of happiness in all future years discounted. By a little algebra, you notice this sum from t to capital T, we can just break out the first term. First term is here. When tau equals t, you just get this. And then this is the same as this sum over the later times, as tau goes from t plus 1 to t. Straightforward algebra. I did change one thing here. I decided to multiply this by gamma in front and divide by gamma here. And again, in algebra, we're allowed to do that. You can multiply this by gamma, divide this by gamma, and that makes the appearance of this look kind of nice. In fact, you'll see this is basically the same as j, only starting from time t plus 1. Put those two things together, it's straightforward algebra. That j at the present time equals u at the present time plus gamma times j at the next time. Your future happiness now is equal to your direct happiness now plus your future happiness in later years. So this is a recurrence relation. J now is u plus gamma j. And this is rigorous as long as these terms are mathematically well defined. If j is infinity, well, this doesn't work out so well. But as long as j is a finite number, then this is straightforward algebra. Now in dynamic programming, we're trying to find the policy or strategy pi, which will maximize the expected future value of this sum j. And we write that as j star is the maximum possible value of j over all policies. So here policy is an argument, we maximize over that argument, and we define j star as the best we can do. And we're trying to find the policy pi, which lets us do the best we can do. And as a practical matter, we have to be able to estimate j star in order to figure out pi. Those are related tasks computationally. Now, if you look at this closely, you'll see this j star is exactly the same as the j star which we calculated when we were working through the decision trees. When I was showing you decision trees, it wasn't just for your economics entertainment. It was to give you an example of what is j star. J star is the number we wrote under there that represents the best we could do, what we expect to do from any given node. Now I'm going to start waving hands a little. This is going to be intuitive, and a lot of you will want to go back to the math books. But this is a little more rigorous than some of the things you'll read in some places that are called theorems. Intuitively, we have a choice of any policy we want. We want to find the best overall possible policies. So, for example, we can choose a policy which is any action we choose at the present time, and then any policy we like for future times. When we maximize, we're maximizing over that large set of possibilities. And so intuitively, that tells us that the best policy we can do now is the maximum of these two terms. This is the happiness we can get in the next time period, but we only need to maximize over actions we take now, and the quality of the states we get into in the future. Okay? So let me explain this intuitively. In the next time period, when you're at x of t plus 1, what is the best you can do? By definition, the best you can do at that time is nothing but the j star. So your total future stream of benefits is u plus that j star. That's the best you can do. And you want to pick the action u now, which maximizes that. Forgive me, it's a little bit hand-waving, but this is the Bellman equation. And this is the most important equation for the whole course. It's the foundation of everything. It says that j star in the present is equal to the maximum over all of the actions you could take now of the expected value of u plus j star in the next time period. Now, if you think about it, if you go back to the decision trees, you remember there were chance nodes and choice nodes? At the chance node, you're taking this expectation value. At a chance node, the value is the expectation value of the j star at the next time period, and we didn't show a payoff along the tree. We could have added that, but people don't do that in decision trees. It makes life complicated. But at a chance node, we compute the expectation value, and at a choice node, we maximize. We pick the action or choice which maximizes what you get in the next chance node. So basically, this is how we are doing the decision trees, but it's a much more general concept. In fact, we really need to look at this equation very carefully, and I'll be looking at it again many times in this class. We need to look at this equation very closely. There are three major caveats here that make this not quite universal. When you prove the theorem that j star exists and obeys the Bellman equation, if you're maximizing utility, that theorem has certain assumptions to it. There are a lot of times in control theory when people tell you, I have proven a theorem that this method is stable, always stable. And when they say that, I ask, what are the conditions of the theorem? When I learned mathematics, I learned a theorem is a statement of the form, if something, then something. And you don't know what the theorem says if you don't know the if. You need to know what are the conditions that must be true in order to get the desired results. And a lot of times people play fast and loose with that. You have to be very careful if somebody says, I've proven this is always stable. Well, what's always? What are the if? What is the condition? In this case, there are certain conditions which are very important. The most important buried assumption here is the assumption we get to see X and we get to act on the state of the world. This is a fully observed system. In practical engineering, we usually do not get to see the state of the whole world. So practical engineering is not really about this equation. It's about partially observed Markov processes. So we have to develop mathematical techniques to compensate for the fact that we don't see the whole world. And I should give you an example of how important that is in decision making in real systems like brains. One of the things we do in system identification or cognitive prediction is we try to build an image of what is the real state of the world. An estimated state vector or belief state. We try to build up an idea of what's out there in the world beyond what we see right now. In neural networks, we do it with recurrent networks. So once upon a time, I knew somebody who proposed a theory that said human beings, our perception of the world is basically a function of what we saw in the last 30 seconds. We have time lags. And that's as far back as our memory goes. I said, supposing there was a human being like that. This guy is running in the forest, and there are a bunch of wolves chasing after him, not barking a lot. or maybe a quiet tiger chasing after him. And he turns around and he runs. 30 seconds later, he doesn't see the tiger. It's not part of his state vector. His policy is a function only of what he sees. He doesn't see the tiger. He stands there. If there ever were humans like that, they have been eaten a long time ago. The important thing is that in order to survive, we sometimes need to maintain an image of the actual state of the world, which is more than just what we see. That's a big part of what we need in practice to get benefit from these methods. And the issue of partially observed Markov decision processes is of enormous importance, not only in the pure mathematics, but in practical engineering. And in practical engineering, we have some very good practical techniques for dealing with it. And the biggest technique is basically have a cognitive prediction system that does your state estimation, or your belief state estimation, so you got the right inputs to your decision. So that's the biggest hidden assumption in this equation, the observability assumption. But there's another important assumption, and that is that this is a finite number. And if capital T is infinity, and if the interest rate is 0, as it should be sometimes, in that case, this is not a finite number. And this is not mathematically well defined. And what can you do? In that case, dynamic programming was generalized by a Stanford professor named Ron Howard. Howard has a very important book on dynamic programming. His book was basically my starting point when I did work on ADP long ago. And Ron Howard's book provides a more general version of the Bellman equation, which is capable of dealing with a case of infinite time and 0 interest rates. But I'm not going to talk about that a lot in this course, because I've discovered there are a lot of people who are really not interested in that. But I am going to talk about, I do talk about this in the Handbook of Intelligent Control. The Handbook of Intelligent Control is one of the 2 most important references for this course. I mentioned the new book by Lewis and Liu. That's really important. Equally important is the Handbook of Intelligent Control from Van Nostrand. I have the citation in these handouts. And in my chapters for that handbook, I actually give you the more general Bellman equation, which comes from Ron Howard. And long ago, when I developed dual heuristic programming, I was really addressing this problem of what do you do when the normal methods do not converge. You can get into a problem I think of as the crossroads of history, where the decisions you make in finite time can put you on a track, like that student example, where forever you may be dead. And it's important when you're in a crossroads situation, you've got to change the way you make decisions. And there is mathematics that lets you cope with that. So that's just a caveat, but frankly most people are not doing that. And if you expand your foresight gradually, you don't really need to use the Howard version of dynamic programming. So I don't talk about that as much. Finally, there's one more caveat about this equation. I'm trying to make it the most general case, except for this infinite horizon issue. This is a very general version of the Bellman equation, but in practice it's usually not that complicated. For example, your payoff doesn't always depend on your actions. It's very common that really you don't need to put the little u in here. And a lot of times you don't need to consider that dependency, and then u comes out of the expectation brackets. Well, actually it may in general. The other thing is, the time is not always a variable in here. In fact, most of the time, when you're approximating the j function, it's not really dependent on t. If you have an infinite time horizon, and the dynamics of your system are not changing, it's a changing system, but the laws, the model doesn't change, and you've got an infinite time horizon, you don't need little t. And there are lots of problems where you just don't need little t. But in principle, this is the correct answer, and you have to decide whether you can simplify it or not. Now finally, for the end of this lecture, I'm going to briefly talk about what is dynamic programming. And of course, I'm going to talk a lot more about it in coming lectures. Dynamic programming is the Bellman equation, but it's also using the Bellman equation to solve optimization problems. In traditional dynamic programming, people follow this flowchart. The user supplies the utility function and an interest rate if there is any. And the user supplies a model of reality. What does the model of reality do? It gives you the probabilities. It tells you the probability of different events, x of t plus 1, as a function of your actions. And you don't see that model in the equation, but when you see x of t plus 1 and you see an expectation value, your model of reality is there implicitly. By the way, I should have put a star in here. Please forgive me, it's an older flowchart. The star is the more correct modern notation. The way you use this equation, the user provides the model that lets you compute expectation values, and you try to solve for J star. And when you solve for J star, the theorem is the optimal policy is to take the right action at each time to maximize this function. So what dynamic programming does is it takes a difficult multi-stage optimization problem and translates it into a single-stage optimization problem, which is much easier. Making decisions for the next 100 time periods is a lot more complicated than making decisions for one time period. You're maximizing over something much simpler than pi, much simpler than the set of u for all future times. You're maximizing over a relatively small set of choices, the choices you face at the present time. So dynamic programming converts a difficult multi-stage stochastic problem into a one-stage problem, but you've got to solve for this function J star in order to figure out the optimal action u at any time. J star, I'm going to talk about more. It isn't only a measure of your best possible future payoffs. It's almost like another kind of utility function. Instead of maximizing u, we're now into the realm of maximizing J star, one time period ahead. And this is very important. This happens in real life. I'll give you some examples. There are a lot of times when there's one thing you care about in the long term, which is your u, and then there are things in the short term that tell you whether you're making progress towards that goal. You can think of J star as a progress measure. And in the next lecture, I'll talk a little bit more about J and what it means intuitively. Because you've got to understand what this function is if you're going to do dynamic programming a lot.